The two, if you were here for the two talks this morning, Raf gave a really awesome talk on the sort of underlying technology for drones. And then Lucas highlighted a lot of the applications that drones can be used for. And in this talk, what I want to do is tell you a little bit about the evolution of a platform that connects those two things. So connecting the technology to the actual application and what it takes to actually bridge that gap, or what we've done so far for that. So just really quickly about Airware, as Lucas said, we're venture-backed, roughly 70-person startup. We're located in San Francisco, and we're building a hardware, software, and cloud platform to develop commercial drones. The story, and I'm going to kind of tell this as an evolutionary story, and it starts my own personal story in grad school, where I was doing aerial robotics research at MIT. These videos are not nearly as cool as Raf's videos, just to set that straight. But basically, you see a couple foam planes there. These are custom built. We were doing some adaptive control work on those. We have a bunch of quadrotors flying around. This was back in 2008 when motion capture systems were just starting to be used. Similar thing, flying a bunch of drones at once. And what we were doing was coordinated control algorithms. And this was the early days of proof of concept of those algorithms in terms of actually flying them in a controlled environment. 2010, things getting a little bit more sophisticated. This is a mobile battery swap and recharge station. And so basically the drone lands on the station and fully autonomously the battery gets swapped and the discharged batteries are automatically charged. And that enabled us to do actually completely persistent missions without any interaction indefinitely. So I think we ran a mission in here for over 24 hours and with no human intervention. Then we started playing around with the actual, variation of the pitch of the multi-rotors, and so you can see in addition to controlling the RPM for control of the drones, also messing with the pitch actuation. And then this could do some pretty neat things, flying super smooth trajectories. Again, this is in a motion capture space, and then could also enable you to do, so that you see here, the drone is actually flying upside down in a half flip. It could also enable you to do pretty cool things like really tight flips, so flipping over without any sort of jump or altitude loss, and then some other cool acrobatics. And then in my own research, basically did some learning from demonstration where you could teach a drone something by just moving it around. The algorithm would find the key points of that demonstration, and then actually re-execute, but with the autonomous system as opposed to the human who was just moving the thing around. So what all these things have in common, and the reason I'm showing you this, is that when you're actually flying these things, things go wrong all the time. This is a little blooper reel of things in our lab, and the reason things go wrong is because these are implemented time and time again, and we're trying to implement the same software with for research, and there's no platform for it. So what I learned was that designing, building, and flying hardware and software for flying robots is soul-crushing, tedious work. And what I really hoped would happen is that someone would make a platform that makes autonomous flight easy, but still customizable. This is Jonathan Downey. He's the founder of Airware. We met as undergrads, and he was on the MIT undergraduate UAV team. And basically what he saw was that most of the teams were just putting black box autopilots in here, and these are the things you could buy off the shelf that were in military drones. And he designed a completely modular autopilot from scratch. We also worked together on the Boeing A160 program, and it was a similar thing. There's lots of really expensive black box hardware that exists, but there was no truly customizable framework. So we eventually got to talking, and what we, and this is an email that we kind of sent back and forth, and basically what we're calling out here is the idea that a product should give you good position orientation data, but allows you to code your own autopilot yourself with an emphasis on flexibility. And so what we ended up doing was creating a series of autopilots, and Jonathan started a company called Unmanned Innovation. Put a core team together, and the idea here was that you had customizable autopilots, and there were sort of three components to this really early system. The first was a core board, and this has sensors and a coprocessor for data fusion and estimation. This is a thing that would go on every single drone, and because it has the core sensors that are common to that drone. In the middle, we had a Gumsticks, which is an early Linux computer that was the size of a gumstick, and you could write your own flight controls applications on here. And so the idea was that the core board enabled you to get the data that you needed without doing all the estimation yourself, and the Gumsticks board was where you can write your own flight controller and do the work. And then there was an application-specific breakout board that depended on your specific application. And so in this case, this is an application-specific board for fixed-wing vehicles. This is for multi-rotors, and this was a really tiny one. These things had different radios, different types of actuator breakouts. And we even put it together. We did a demo on this is an earlier version of that variable pitch actuation that I showed you earlier. So we put this together, and this was solving the problem of researchers, essentially, to have a platform that you could easily just drop your own autopilot code into, because that was the problem that we cared about. So we ended up going to a trade show. This is the big, it's called the AVSI trade show. And we went there, and we pitched this as, look, all you have to do is drop in your own autopilot code, and you can do all the applications you want. And you can imagine how many customers we actually got from this. It was essentially no one that wanted to buy it. And that was because people didn't actually care about writing autopilot code. They wanted to use the drones to collect the data that they cared about. So this is sort of an evolution of building out the platform. And this first thing, all we had was really an autopilot hardware and software that people could customize. But that was not nearly enough for anyone to do important things with drones. So we said, okay, well, why don't we add extensibility to many different types of aircraft? So we'll do the work of customizing this for different types of multi-rotors and different types of fixed wing. And so here you see just a few. This is an octocopter. This is a quad rotor. This is a really long endurance quad rotor that can fly for 60 minutes. This is another octo. And this is a fixed wing vehicle. These are all drones that are used today for commercial purposes, but have different types of flight dynamics and require different software to actually run these. So what we did was take the original concept of that sort of monolithic flight controller, and we broke it up into something that was modular. So now in the center we have the flight core. This is a thing that again has the inertial sensors. It has barometric pressure sensors. But now instead of everything being on one unit, we separated the hardware so that it could be applied to more than one different type of vehicle. And so, for instance, a GPS module is now a separate, an airspeed module, which multi-rotors don't need airspeed modules, but fixed wings do. So why not make that a separate piece of hardware? Same thing for the actuation module. The different drones have different numbers of actuators. They have different types and interfaces. And then an air data link module. This is essentially the radio that connects the vehicle to the ground. And this is different by application. So by country, these have different frequencies. You might be inspecting a tower where you only need half a kilometer of range, or you might be inspecting a pipeline where you need 15 kilometers of range. And so we broke this up into many different components, and then we essentially made it so that it's really easy to drop these into different pieces of hardware. So you can drop multiple actuator boards and just daisy chain them with this hardware architecture. You could replace the GPS board with a really high accuracy one if you were doing surveying. You can change this data link module. Everything was really simply plug and play, and this is what enabled different applications, to specify the exact hardware for different applications. So just to go in a little bit to the actual technical underlying architecture here as a sort of building block for the application framework that I'll present a little bit later. This is essentially a block diagram now of each one of these different pieces of hardware. And every blue box here you see is either a software thread or a driver. And so when you're trying to make a platform, all these things need to be totally interchangeable, and the software complexity really explodes quickly. And so in the importance, if you're familiar with Robot Operating System, this is a development framework that the robotics community has adopted. And what it is essentially just middleware. It allows software components to publish data, subscribe to data, and make remote procedure calls. And so the sort of concept here is that this block, for instance, is the inertial estimator. This is the thing that takes the sensor data and fuses it together and creates a state estimate. This needs to subscribe to data that's being published from the GPS board. And then the output of the inertial estimator goes to control algorithms. The controller needs to know where it is in the world so that it can do closed loop control in the vehicle. And so what we found was that a really key part of building extensible systems is the middleware that you put in between all of the different software and hardware components. And in this case, these not only is the middleware connecting threads that are sitting in the embedded code together, they're also connecting different pieces of hardware together over different buses and topologies. So a lot of our development effort actually went into making this middleware layer that would enable different hardware and software components to talk together seamlessly. And the sort of theme here is that this is something that as a user of commercial drones, you would definitely not care about and you would never want to do. But it's a really important underlying piece of the framework that really should only be done once and be done well. So we implemented this modular framework, and now we are able to fly lots of different types of drones and to do them in a similar way so that there's only one flight controller. It's very easily tunable. You see a few videos here of different types of commercial drones, and you can use the same framework that you used for multi-rotors to be used for fixed wings as well. And it all relies on a modular underlying architecture that you shouldn't have to develop time and time again. You should just be able to use it for your application. So the next sort of step in that evolution is this multi-vehicle architecture. So we went from having something that is just an autopilot, just has flight control code on it, to something that is modular and can be extended to different types of vehicles. So then the next question is, well, people actually have to use these things. And when humans use machines, they have to have an interface for using them. And what we noticed was the user interfaces for drones, this was roughly 3 years ago, were fairly terrible, I guess you could say. So there's lots of busyness on here, tons of text that you have to put in, lots of colors. This one is especially egregious. These are, and this is supposed to be the real-time interface for the human to understand what's going on with the robot to the extent that they need to. And these are also the interfaces through which the human has to program the robot's behavior. So this is a really, really key element of the autonomous system that's often overlooked. And so the next step in the platform was to say, well, people have to use these systems. Well, why don't we make a really streamlined user interface that allows people to use it very simply. So we essentially came up with two pieces of software. One is called the ground control station. This is the real-time interface that allows the human to plan autonomous missions, upload all of the data to the aircraft, upload contingency procedures that enable the aircraft to know what to do if a radio link is lost, and then configuration management software. Configuration management is, again, one of those things that seems boring, but for a platform that can control many different types of vehicles, if you configure the vehicle improperly, this is one of the leading causes that we've found of flight incidents, is actually configuration. And so designing tools that enable you to smoothly operate the vehicle, but also to configure it, are again things that are required for an underlying platform that you should never have to develop yourself if you want to use drones. So I have a quick video here of just to give you a flavor of what the Airware ground control station looks like. The first is a really intuitive flight planning interface. You set a geofence, so this black line around here is essentially the fence through which the aircraft cannot fly, and that goes all the way down to the embedded software level. What you saw there, real quick, and I'll replay this. What you saw here is not only the geofence, but also contingency plans. So these are the pre-programmed flight behaviors that if your aircraft loses GPS, or if you lose data link, or if it flies outside of the geofence, you need to tell it what to do. So these make it very easy to configure those, and this is something that was typically very difficult to do in previous autonomous systems. So now what you see here is a user changing, for instance, this photo survey path. It's very easy. You can configure the survey to collect the data. And the idea here is that you want to set it up so that when the person arrives at the site, all they do is press a button, and the vehicle will take off and collect the data that it needs to take. So you see a plugin interface that's configurable. And really, there are only 6 buttons here. And this is another important thing. As Lucas mentioned in his talk, the #1 cause by far of aviation-related incidents is human error, is typically pilot error. And so for unmanned systems, it's even more difficult to control the vehicle because it's flying somewhere and you're on the ground and you don't have much insight into actually what's going on. So the philosophy, and this is the trend that most drone technology is going, is to automate as ruthlessly as possible so that the operator only needs to step in when absolutely necessary. So in this case, the operator only has 6 buttons. One is to activate the vehicle. Another is to pause the vehicle while in flight. Another one is to abort, and this is in the extreme case when you need to bring the aircraft down right now. Return to home and land now, and then a few launch and go to buttons. And these are the only inputs that the human actually has to the system. And the system is programmed so that once it takes off, it has all the information it needs to not only launch, collect the data and land, but it also knows what to do in contingencies. And again, it will never fly out of this box. So the video that Lucas showed earlier of the guy flying his consumer drone over an airport is something that can happen with this system, cannot happen, because you've programmed this geofence. And at the embedded level, that geofence is enforced by the underlying flight control software. Again, this is a safety feature that is absolutely critical for commercial drones, but that you would never want to implement yourself if you just want to use the drones or do applications with them. So again, just coming back to the middleware, middleware is really important because now, in addition to the autopilot and the various pieces of hardware, now you have a ground control station that also has lots of software components, and they need to talk over the same thing. So the next sort of step in the evolution of this platform was a streamlined user interface that allows humans to actually use these systems for real applications. So now we'll get to the sort of relevant part to this conference, which is the application framework. What you see here is really a system that will just fly the drone. But flying the drone is not enough. No one, hobbyists want to fly drones for fun, but businesses want to actually use drones to collect data. And so to collect data, you need sensors. You need to customize the actual flight path of the aircraft. You need to tell it what to do to put it in the position where it will collect the data that it wants. And then you need to actually record the data somewhere. And we found that with the system that we have here, we couldn't actually do that. We could just fly the drones. And so it would require you to add on your own application-specific software. So the next sort of step in the evolution of the platform was the application framework. So on this side is the side that I sort of already explained. This is the flight, what we call flight critical. This is a closed real-time operating system. It has custom Airware flight software on it. It's sort of the hub for certified flight hardware. And it's important that the flight hardware be extremely reliable and certified, and you don't want that to be customized from application to application. I don't want you messing around with the GPS code or the inertial estimation code. It's also compliant and certifiable. So that's the flight critical side, and this side is relatively closed. It's closed because, again, we need to ensure reliability, and it's closed because these are things that you probably wouldn't want to change from application to application. Now, on the other side, this is connected with a data bridge to what we call the application core. On this side is completely open. So this is Linux, whatever distribution you like, with app management. We've put middleware on here that basically enables apps to talk to each other via simplified publish, subscribe, and RPC mechanism. So this also, and what that simplified mechanism allows different apps to talk together, and I'll show you an example of a vertical inspection application for the actual software that you would develop. This offers tight but protected integration with the flight control system. So this is one of the trickiest bits about making a platform that people can use for commercial purposes with drones, is that if you're in Raf's talk earlier, you probably, there's lots of theory that goes into how to actually control things autonomously. And it's very delicate to the way that you tune it, the way that you respond to different types of disturbances. And so but the applications still need to tell the drone where to go. They still need to control the drone. So what we've done here is created a high-level flight control interface where all of the low-level closed-loop control is done on the flight critical side. And again, that's closed to the application developer. But the application developer can command the aircraft by requesting control of it, and there's a priority queue of control, and then offering high-level maneuvers or control requests that go from the application side to the flight controller. And any app can do this. And the way that we're able to get away with this is that these requests are very high level. So these are things like launch, or fly to a waypoint, or land, or do a photo survey. They're high level behaviors that the app gives the parameters to, but doesn't actually need to do all of the low level closed loop control for itself. And this is really important in actually making these systems customizable for people who aren't drone experts or professors of flight controls. There's also onboard apps that are, again, in an open framework that allow you to connect to user interface plugins on the ground control station. And really here, we're trying to embrace open source for applications while still ensuring safety. And so you can't, application developers, moving into the future for drones, we don't expect them to be drone experts. And so we want to enable them to have a sandbox where they can develop applications and test things, but not have to worry about risking the safety of the drone. So here's an example of the software as an app developer that you would actually write for an application such as vertical inspection. So in this application, what you want to do is autonomously fly a drone around a cell phone tower. Today, the way that cell phone towers are inspected is extremely manual. You have people climbing up on ropes. It takes about half a day to do one cell phone tower. And it's actually very dangerous. So in the United States, this was one of the most dangerous jobs in 2014, with almost 20 people dying just climbing on cell phone towers. With a drone, you can fly around. You're collecting the same data. The data that the tower collectors are actually collecting is just point-and-shoot cameras. So they'll climb up on the tower, and they'll take pictures of things, and then the pictures will be manually cataloged into a very ad hoc report. The drone offers a much better way of doing this. If you can fly around this tower autonomously, you can take enough pictures to generate a 3D model of the cell phone tower, and that 3D model can then be annotated. There's sort of interesting constraints for these inspections. The reason they do the inspections primarily is so that when they want to put new equipment on the tower, they need to analyze the structure of the tower itself. So they need to know, what is the wind loading from the current antennas that are on there? Can I put more on there? What is the weight loading? So a drone has the ability to fly autonomously around the tower, generate a 3D model. You can annotate that model with the different antennas that are on there, with the lengths of cable. You can do precise measurements. And this is something that you could never do with the manual inspection. So how would you use the Airware platform to actually develop an app that would autonomously inspect a cell phone tower? So you would start with the sensors that you need. And in this case, you'll need a scanning laser. And this is a basic range measurement that is scanning. And this will allow you to stand off from the tower and to ensure that the vehicle is not actually going to bump into anything. Because if these towers go down, it represents millions of dollars of lost revenue for every day that the tower is in operational. So failure is sort of not an option here. So what you would do is write a driver for the laser scanner that spoke the specific language of the laser scanner, but then publish the scan data in a way that all of the other apps can understand. And again, this is the importance of middleware. So you'd write a driver for the laser scanner, and it's publishing laser scan data. It publishes the data to a flight control app. And what this app will do is subscribe to not only the laser scan data to know what are the obstacles around it, but also the navigation data that's coming from the drone itself. So your app needs to know where it is in order to fly around the tower. And to do that, what this app will do is subscribe to, for instance, the GPS data. It will subscribe to the velocity data. It will subscribe to the laser data, and it will fuse all that information together. Seems like a complicated process, but actually in our own prototyping, all of the apps that you see here, we just developed in Python, and using a really high-level interface to everything else. So you take the scan data, do obstacle avoidance, take the navigation data, and from that, what you need to do is publish commands that go back to the autopilot. But the system makes it easy to publish commands so that you can, for instance, launch and then transit at a minimum altitude. So that's one of the maneuvers that an app can request of the flight control. And what that lets you do is, as an app developer, specify a safe altitude and a location that you'd like to go to. And what the flight controller does is take care of all of the low-level dynamics of flying up to the safe altitude and transiting over to where you need to be. You can then send it a maneuver to descend at your location and ascend. And what you can do during these is take photos. So the next app that you would write is a driver for a gimbal and a camera. So lots of off-the-shelf gimbals exist that will point a camera, lots of cameras that exist that will take photos. And what you would do is write the specific software to talk with those things, but again, present those capabilities to the rest of the system. So as the flight control app is flying up and down the tower, it's commanding the gimbal to point at the location on the tower that you'd like, and it's completely configurable. And also, commanding the camera to take photos at intervals that can be configured beforehand. So as an app developer, I've been able to write apps that talk to my specific sensors. And these sensors, again, have nothing to do with the actual drone itself. These are the sensors that are important to me in my application. So I can write drivers for those. I can write a flight control app without really knowing how to do flight control. I just need to know high-level primitives. And then the sort of last element of customizability as an app developer would be some type of user interface. So this is the same ground control station that I showed you earlier, but what we've implemented is a plugin interface so that you can develop plugins in a separate project, compile them to a DLL, and then drop them into a folder that gets loaded at runtime. So for instance, in this application, we've designed a plugin that enables you to configure the inspection by walking the drone around the tower and placing it down and saying, okay, I want to inspect this column right here. Okay, I put the drone down. This is going to be my landing location. So it allows you to not only configure the inspection, but it will then enable you to control the inspection. So it has a button to actually launch the inspection or to pause it or to return home and land because the battery is getting low. And so you'd write an app for this, and with this app framework, you can write the app completely independently of the ground control app that we've written to be reliable and really easy to use and streamlined. And then this app, again, through the middleware that we provide, has access to the data that's going on all these other apps. So this is an example of how you can write an application for a fairly sophisticated task, which is to fly around a tower, without really knowing too much about the underlying drone technology, because you shouldn't have to in order to get the data that you want. So that's the sort of next element in the evolution of the platform. We have the flight hardware modular so that we can fly more vehicles. We have the ground control station software, and now we have an application framework that allows developers to come in and develop application-specific software without being experts. Still, this turned out not to be enough because one of the major pain points for companies, and Lucas touched on this in his presentation, was an actual workflow. So there's not only one cell phone tower that I have to inspect, there's 800,000 cell phone towers in the United States. So for a company to realistically scale drone operations, there needs to be planning and workflow software that enables them to plan a job and then assign it to one of hundreds of operators with drones, and then to get that data back in an organized way. And so that leads us to develop a cloud platform. And so what you see here is the Airware cloud platform, and there's a few relevant features. One is that things are organized by jobs and by projects. So as a cloud planner, I create a project. And this project holds all of the jobs for, say, a customer of mine, Allied Tower, or a farmer who wants to inspect different areas of their farm. Within that project, you can create jobs, and these jobs may be different things. So on a farm, it may be mapping a field with a multispectral camera, or it may be inspecting a fence line, or it may be surveying the lake to see what the water level is. So I can create a job. I'll let this play here. There's also some other things like managing my fleet, and if you have a fleet of drones, managing them actually becomes quite difficult because they break, they need to be inspected. And I can also manage the personas, so I can assign pilots or I can assign people who are allowed to change the configuration of aircraft. So this is an example view of a job, and what you specify is not only the data that needs to be collected, but also the safe region that the drone should be able to operate in. And so in this case, the planner has highlighted what we call a geofence over a farm, and that gets set at the planning stage. And this is another really important feature of safety, is that in order to ensure that drones will not fly wherever they want to, or to allow operators who may not be following the rules, the geofence, the limitations of the drone, are set before it even takes off. It's set in the cloud by an authorized planner. And then what can happen is that geofence can be thrown through a compliance workflow. So this can either be sent to a regulatory authority to check for other drone operations that may be happening in that area. Or it can be sent to your insurance company to say, this is the area that I'd like to fly in. Is this compliant with my insurance policy? So you can tie this safety into different elements of actual commercial drone operations. And then what will happen is that this job gets completely planned in the cloud. It gets assigned to an operator on the ground. So the operator doesn't know anything about the data they need to collect. They just know how to collect it. And so that will get synced. The operator will download that entire what we call flight package. They'll press a button. The data will be collected. And then once the operator has collected the data, it will all be reattached to the job in the cloud. And this is one of the major pain points of commercial drone companies today, is that these things collect a massive amount of data. You can collect hundreds of gigabytes of photos over the course of a week surveying a farm. And so organizing all of this becomes really important. So the thing that the Airware Cloud enables you to do is automatically attach any data that you collected during that job back to the original job that was planned. So at the planning office now, I've abstracted the problem away of sorting and sifting through all the data that I was collecting with my drone. And I can say, okay, well, I planned this job. This data magically appears once the operator has collected it and uploaded it to the cloud. And now I can start to do analytics on it to get closer to the paying customer who wants the data. And in this case, and you've probably seen a few of these before, but this data you can put into planning tools. There's lots of these tools that come off the shelf. This is an example tool called Pix4D that will do a process called photogrammetry to take two-dimensional photos and create an extremely detailed three-dimensional model of the, an extremely detailed 3D model of the farm. So from this thing, you can measure water levels, you can measure crop heights, you can do multispectral NDVI analysis. You can see if your fence lines are broken, you can see if dams are broken. This is an actual farm in Petaluma, and we were able to see trees that had fallen over a road. We were able to see a dam that had a big crack in it. We were able to measure the exact water levels of the creeks and reservoirs. And one of the important things about this is that you can't just put images into this processing algorithm. You need metadata for the images. So in this case, what you see is that we've initialized the algorithm with the exact position and orientation that the photo was taken. This also represents a real pain point for commercial drone operations, however. So let's say I'm the operator, I've taken a bunch of photos with my drone. If those photos aren't tightly connected to the flight logs that told me where exactly they were taken, then the data is essentially useless. And so one of the really important parts of collecting data for commercial operations is having everything packaged together in a way that it's compatible and can be post-processed. So in this case, the Airware Cloud will take the flight logs that record when each picture was taken and output a file of metadata to say that this picture was taken at this exact GPS location. It was taken when the vehicle was pointing in this direction, and it was taken at this time. So metadata is really important. And so this is sort of the final element of this platform. So we've gone, from sort of nerdy hardware that you can drop your flight control code into, to a modular system that now can fly different types of aircraft, a user interface that will enable the human to interact with the robotic system in a streamlined and safe way, an application framework that will enable developers to come in and customize just the parts of the problem that they care about by developing apps. And then finally, a cloud management platform that will enable enterprises to plan the data that they want to get, assign it to operators on the ground, and then have the data come back in a way that's usable for analytics. So this is sort of an evolutionary look at how the platform evolved. But for people who want to actually want to make money operating drones, this is probably not the best way to look at it. And so a different, sort of an alternative interpretation of what happened. And this is, I'm an engineer, I'm not a business major, but I can imagine in planning out how to make money from something, you start with raw ingredients, and in this case, this is an aircraft with sensors. And what you want is to somehow get to the paying customer. So how do I take the raw components and make money from them? And so for commercial drone operations, you can sort of view that evolution that I just showed in a different context. So I take the raw ingredients, and a service provider will then integrate the aircraft and the sensors. So they have to take the aircraft and the sensors, put them together into a flying package, and then they need to plan the job. So the farmer calls up, I need to do planning. In the next step, I need an operator to actually go and collect the data. So you need a data collection workflow. So we've gone from raw ingredients to an integrated aircraft to a job plan, and now a data workflow. But having the data is not enough. You then have to do analytics on the data and then create reports and data processes. And that then finally gets to the paying customer. So in terms of commercial drones, this is the value chain of how money gets all the way back through to each component of the system. So we started thinking about this, and if you look at that sort of evolutionary, that sort of technology evolution that I just showed you of the platform, you can actually think about it in a different way. You can say that each part of the platform is actually addressing a part of this commercial drone value chain. So in terms of the actual integration of aircraft and sensors, this modular framework makes that really easy to do. In terms of job planning, you've got the Airware Cloud that can easily take a request from a customer to then plan a job. In terms of the actual data collection workflow, this is something that we've now standardized. You can create projects and manage users. You can set up the vehicles using the configuration software. Create jobs, you can get approvals, create flight plans, actually fly and acquire the data with the ground control station, sync that data back to the cloud, and then offer that up back to the service provider in the first place, who will do analytics, create data products, and get that to the customer. So this is sort of an alternative way of looking at it, and this is, people like Lucas and Aerialtronics are starting to look at the problem this way, which is, how do we provide valuable information to customers who are actually going to pay for it? And it's sort of in contrast to a lot of the hype that's going around with drones, which is, how do we do cool things with drones? This is really the way that it's going to have to be looked at in order for drones to proliferate. And these are the types of tools that we'll need in order to make that happen. So in terms of actual application developers, there's lots of places on this value chain where application developers can add a ton of value. And so just to name a few, the integration of different aircraft and sensors, so I walked you through that sort of vertical inspection application. There's lots of places in there where software developers can add drivers for different types of sensors, or can make algorithms that autonomously inspect things like cell phone towers or bridges. There is lots of area for improvement right now in approval. So for instance, in the United States, the FAA, they don't really know what a cloud is. They still think the cloud are things that planes have to fly around. But there's lots of places where software developers can come up with workflows so that a flight plan can be automatically approved by, say, the FAA or by an insurance company or by your organization. So there's lots of plugins that can be written there. Creating flight plans, there's lots of areas of customization, automation here. So taking a really large area to be surveyed and breaking it up into lots of different missions is an example of an application that could be written. Flying and acquiring the data, also an area that needs to be customized by the application. There's lots of opportunity here for app developers to come up with new and different ways of collecting the data. For instance, we've only shown you sort of flying over a field when you have GPS, but there's lots of interesting applications where you might want to fly inside. So let's say you wanted to do a structural inspection of oil and gas infrastructure. There's lots of pipelines that need to be inspected. Oil derricks, where you'll be flying under the derrick, where you don't have GPS, and you'll need to use vision to actually navigate the drone. There's lots of areas there where getting the data in different ways is still largely an open problem. Lots of work to be done in syncing with the cloud, and by this I mean that there's so much data to be collected that it can't possibly be all sent up to the cloud. There needs to be pre-processing that happens on the actual aircraft to pull out the relevant features of the data and reduce the size of that data set to something that can be transmitted over sometimes a really lossy link. In the example of oil derricks, there is no internet connection. The only thing that they have is a SATCOM link that is extremely low bandwidth. So to get data quickly from an inspection of an oil derrick to somewhere where it can be processed requires a vast simplification of that data to only the relevant features. So lots of automation and machine learning that can be applied there. That sort of ties right into the analytics. All the data needs to be analyzed somehow. And that's where a lot of app developers can come in. And in making the actual data products is another place where even after you've analyzed the data, putting it in a report that is understandable by a company who needs to use it is often fairly difficult. So these are areas where app developers can jump into the sort of world of commercial drones, and thinking about it in this way, which is essentially a value chain, we found to be extremely helpful and shape where the best effort should be. So I just wanted to sort of conclude the talk with going through a few of the applications. We've seen a few today, but some applications that maybe you haven't thought about or that are not possible today. Wildlife surveying is one that we've done a little bit of. So the way that wildlife are surveyed today is literally with a pilot in a plane and then a person with a clipboard and a pair of binoculars. It's extremely expensive, it's dangerous, it's hard to keep pilots because they get bored because they're just flying over wildlife sanctuaries day after day. And so it's difficult to actually collect data about endangered species from an aerial perspective. We actually took a team and we went to Kenya to the Old Pejeta Conservancy to monitor endangered white rhinos, the northern white rhinos, and what essentially they hired us to go out there and do was an anti-poaching mission. So we would go out there, find the poachers, determine how they're getting into the park. But once they saw the data that we were collecting from these drones, they said, well, we could use this for much more frequent collection of data. So we can do these surveys purely from drones, and we can do them every week instead of every year because it's really expensive to hire manned pilots. And this would give them much more actionable insights. Avalanche rescue is another one. Right now this is extremely dangerous. You have to send a helicopter out. Why not send one drone, or why not send 20 drones? We did a rough cost analysis for the cost of one of these typical helicopters. You could buy, it was between 20 and 30 highly reliable commercial grade drones, not to mention the cost of operation is orders of magnitude less, and the risk to human life also much, much less. Bridge inspection. This is how bridges are inspected. It's kind of scary because this machine is often required to inspect the underside of bridges, the bridges that we drive on every day. And I had sort of thought back, and I can't remember one time when I've ever seen one of these machines in my own actual driving, which is a little bit scary because that probably means that bridges aren't being inspected very often because it's difficult to do. There's technology that would enable you to use a drone to inspect bridges, and again, there's some parts of this problem that are still open, like how do I fly under a bridge that doesn't have GPS? But there's all the sensor technology that is there. There's research that's been done in actually navigating, and now it just needs to come together into an open or into a commercial drone solution. Quarry accounting, Lucas already actually went through this, but surveying is the old way of doing quarries. It's very time consuming. You can fly a drone in a few hours, do exact volumetric analysis of the quarry. There's people who are doing more interesting analysis on these too, where you can analyze the shape of the roads and do statistical data to not only do better accounting for the rocks, but also save fuel for the vehicles that you're driving around. Structural assessment is another huge thing. In San Francisco, where we're located, there's earthquakes fairly often. And so there's an example in the research world of a team from UPenn who took a drone after the large recent earthquake in Japan, took a drone to a structurally damaged building, flew it around, and were able to generate a very detailed 3D model of the inside of the building that could then be used to do a structural assessment. So they could do this first. They could also search for survivors while they're doing it and assess the structure of the building before you actually go in and put people in harm's way. So another application for drones that hasn't seen wide-scale use, but the technology is there. Telecom satellites is another really interesting one. It's very, very difficult to put things into space. It always will be and always has been. And now people are looking into using high-altitude, long-endurance drones to act as essentially planetary satellites. So instead of putting a payload into space, and once it's in space, it's there forever, you can't recover it, why not put it on a high-altitude drone? Where you can still use solar energy to power it, but once the equipment either breaks or needs repair or is outdated, you can just land the drone instead of leaving the equipment in space. So another interesting application area. Gas leak detection is another sort of area where right now it's extremely manual. This is literally how utility companies go around and measure for gas leaks. It's a person with a little probe that they need to put it right next to a gas meter. There's technology now where you can put very sensitive gas sensing equipment on a car and drive around a neighborhood. Well, why not put that on a drone that can fly over entire neighborhoods and find small instances of where there might be a gas leak and then target the inspections to those areas. And then finally, another sort of interesting application is cruise ship safety. So people fall off of cruise ships all the time, and it's often very dangerous. Imagine when someone goes overboard on a cruise ship, deploying a drone right instantaneously with an IR camera to go and look for the person so that it can be located right away and help can be sent. So these are not applications that you typically hear about in sort of the mainstream drones, but examples of places where things in real life that you might not think drones can be applied to, but the technology is there and it's really just waiting for application developers to take drone platforms and technology and turn them towards really useful things that we haven't thought of. So that was all I had, and I'll take any questions.
Thanks, Buddy, for explaining very clearly. Any questions? Yes?
Thanks, Buddy. My name is Shyam. Well, the question I have is, as far as Airware is concerned, I think for FAA clearance, it will be much easier for you. But as far as other companies are concerned, what do you think is the differentiating factor in terms of cost and stability of the platform, especially the autopilot? Because I saw a couple of years ago, I think in Airware it was pretty expensive, so that was my question.
We're trying to bring down, one of the things we're trying to do at Airware is change the cost structure. So typically the way that drones have been purchased is you pay a really large upfront amount for the technology. So you're paying for the hardware and you're paying huge margins on it because that's where companies are making their money. What we're starting to shift to is a per use based model for pricing. And so that means that we're trying to get the hardware in your hands for as low a price as possible initially, but then essentially share the revenue that you're making with the drone. So charge on a per use basis, much like cell phones. So this is exactly what cell phone companies do. They'll subsidize the initial purchase of the equipment, but then you're paying on a month-by-month basis for actually using the data and using the services. And so that's where we're trying to take the actual revenue model so that we can structure the cost of these systems in alignment with the people who are actually using them and making money with them month over month. But it can be fairly expensive, but you'd be surprised at how low this sort of initial cost can go.
Yes, and especially if you think of inspection, sometimes you need very expensive sensors as well. So we hope that the price of sensors goes down as well. Good cameras can set you back 10,000. Well, hyperspectral, $50,000. And
when you're thinking about it, it's really not it's not how much you paid for the system. It's how much money you made with the system. And that's the thing. That's what we're working to enable people to make money with these systems in a way that's scalable. And so hopefully the initial cost won't matter as much if you're making or saving other companies millions of dollars a year.
So get a good business plan. That's a tip. Any other questions? Yep.
Thank you so much for the inspiring talk. But apart from the technological wheel of this presentation, I'm also interested in what you achieved so far as a startup. So you mentioned that you couldn't sell your first product. So looking back to the timeline that you just showed to us, I mean, how did it develop? I mean, at what point in time that you started to get some interest and you started to sell your products to the customers in the market?
So of that timeline I showed you, the 1.0 product came very late. And so right now we're only, I'd say, about 4 months ago, we did our first release of the entire platform. So now we're actually still in the process of evaluating market fit. We have initial customers who are starting to integrate. We don't make the actual aircraft, right? So the first thing that needs to happen is that aircraft manufacturers need to adopt the platform and start using it. And that's the stage that we're at right now. But there's lots of uncertainty. So one of the reasons why I showed this is because we're constantly thinking about connecting the dots to the technology to the actual application and the customer. But that's still something that if anyone tells you they're making, tons of money with drones, they're lying to you. There's still lots of questions that have to be answered. There's compliance issues that need to be approached. And we're really still in sort of the proving stages of how you can take an application like this and use it for applications. So it's still very early days, I'd say.
Do you already have gotten FAA approval, or are you still working on that?
The actual rules, the FAA hasn't come up with the rules yet. Yeah. They've released a draft set of rules. It's called an NPRM, basically a proposal for rulemaking, which could take, people estimate, between 12 and 24 months to actually get put into law. What we have done is taken that draft set of rules and integrate many of those features into the system so that by the time those rules become law, which they're expected to be, we'll kind of be ready for that. But a lot of the things that you see, the geofencing, the sort of approval workflows of the actual geofence. These are things that are already in existence in countries in Europe and around the world that we've integrated into our platform so that making your system compliant will be as easy as possible. So if you have to take your geofence and send it to an agency via the cloud, we have the APIs to do that. And we're working with, for instance, NASA, who has a project called UTM, which is Unmanned Traffic Management. And they have a cloud server that's sitting there waiting for approvals to come. And so we've been doing some testing with that.
Just another one. You had that planning on the mission planner programming interface.
Yep.
Have you planned in to support programming of third-party sensors integrated with the drone, and setting parameters for those and changing timing when something is triggered on the third-party sensors and so on?
Yeah.
Is that thought in?
That's sort of the way it works now. So you would develop an application, specific software that would drive the sensor. And then in the cell phone tower example, that's actually how it works. So that the control app was triggering the camera to take photos. The camera app was actually just listening for someone to tell it to take photos. So that's sort of the architecture of the system as it is.
Okay, buddy, one last question. Can you share a little bit about the fund that you guys just started for developers? Because that might be interesting too.
Yeah, so what we've done is gather some venture backing and created what's called a commercial drone fund. And so what this basically means is that we're looking out for companies who we think have a lot of potential in the commercial drone space, and typically small companies that are just getting started, and have an idea or an early prototype for a product, and we're connecting them to Silicon Valley venture backing through this commercial drone fund. So if you have a company, you have an idea for a company, and you're looking for funding in the drone space, you should go to our website. There's a page for the commercial drone fund, and we're looking through all these, picking out things that we think are promising for the industry, and then connecting them to Silicon Valley venture capital. So trying to seed the market.
Okay, thanks, buddy.
Thanks very much.